Hi, now we are going to talk the second part of rotational motion. Where we are going to talk completely about moment of inertia. You consider a rigid body, irregular shape, where it is capable of rotating through this axis XO, X dash. XO, X dash, it is rotating. You have got different particles at different distances. R1, R2, R3, R4, mass M1, M2, M3, M4, M5, etc. R1 is the distance of the first particle from the axis of rotation, R2 is the distance of the second particle, etc. You calculate kinetic energy of rotation, EK. Kinetic energy basic formula for all the particles we are writing, sigma half mv square. One particle means mv square. All the particles sigma mv square. EK is equal to half first particle m1. V is equal to r omega. This is rotational motion. Rotational motion means linear velocity is replaced by product of angular velocity into the distance r. So we can write V square as r1 square omega square. Second particle m2 r2 square omega square, etc. Nth particle half mn rn square omega square. Sir, why we are putting for all the cases omega? Why not we are writing omega 1, omega 2, omega 3? When the rigid body is rotating, all the particles are rotating with constant velocity. Velocity is constant because the particles are inside the body. You consider a giant wheel where so many persons are sitting. When the giant wheel is rotating, the persons are having different mass. But all the persons are moving in circular path with the same velocity of the giant wheel. Same case. So omega is a constant. So we can write EK is equal to rotational kinetic energy. ER we can put, no issue. Rotational kinetic energy. Omega square by 2 constant M1 R1 square plus M2 R2 square, etc. Mn Rn square. So this is a summation series. So we can write ER is equal to omega square by 2 sigma. I is equal to 1 to n. I is called index number. Starting with 1, ending with n. So we are putting I is equal to 1 to n. Mi Ri square. The sigma Mi Ri square here, sigma Mi Ri square, we call it as moment of inertia of the body. Product of mass and square of the distance from the axis of rotation. That is moment of inertia. Therefore, ER is equal to what? Half I omega square. Half I omega square. Half mv square, normal kinetic energy, Instead of m, we are replacing by I. Instead of v square, it is replaced by omega square because it is a rotational motion. Correct, Amma? Basic unit of I, dimensional formula of I. Unit is mass into distance square, kilogram meter square. Dimensional formula, mass capital M, distance square L square. M L square. Okay, fine. Next, radius of gyration. When you consider moment of inertia equation, that is I is equal to m1 r1 square plus m2 r2 square etc. mn rn square. Consider this equation. For identical particles, assume all the particles in the rigid body are identical. Definitely the mass will be the same. M is constant. Therefore, I is equal to, I can write this as sigma I is equal to 1 to n mi ri square. So take m outside, m r1 square, m r2 square, m rn square. So m constant, take it out. R1 square plus R2 square, etc. Rn. You multiply by number of particles and you divide by number of particles. N is the number of particles present in the rigid body. You multiply and divide by n, so the value will not change. One particle mass is m. We have n particles in the system. So I can say nm is the total mass. Capital M. Total mass. K square. I is equal to mk square. Where K square is R1 square plus R2 square Rn square by n. K will be root of R1 square plus R2 square plus Rn square by n. So it is nothing but root means square distance. Root mean square divided by number of particles. So root mean square distance of all the particles from the axis of rotation. That is called radius of gyration of the rigid body. Unit, dimensional formula. There it is root mean square of distance. Distance square, m square, that is meter square. Root you are putting, so meter. Dimensional formula for distance or length is capital L. Unit and dimensional formula of radius of gyration. Correct? So moment of inertia of the rigid body, in that radius of gyration is a subpart. Now we are going to talk moment of inertia of a uniform rod. Moment of inertia of a ring, circular ring. Moment of inertia of a disc. Three important moment of inertia of the object we are going to talk. moment of inertia of a uniform rod. You consider a rod of length L through the center. Center means where the center of mass is situated. Along that we consider that is called the origin. When you say the length is L, left of origin it is minus L by 2, right of origin it is plus L by 2. You are considering a small portion dx, which is at a distance of x from the origin, that is x from the center. Consider the mass of this small portion as dm. Moment of inertia of the small portion is di is equal to, what is moment of inertia? Basic formula, mass into square of the distance from the axis of rotation. This is axis of rotation. So mass is dm, axis of rotation is x square. Here we are going to introduce a new term. Let lambda be the mass per unit length. Mass per unit length. That is lambda is equal to total mass by L. dm is the mass of the small portion. Total mass, if you want, means it is capital M by L. Capital M by L is the mass per unit length of the wire. Mass per unit length. Okay. So, in the case of smaller part, for the smaller part, dm I want to calculate. dm, what you will calculate? Lambda into dx. Sir, you see here, lambda is m by L. So m is lambda into L. This is for the entire rod. I want for the smaller portion. So lambda into smaller portion distance is equal to smaller portion mass. So dm is equal to lambda into dx. Simple. M is lambda L. Like that, dm is equal to lambda into dx. That's all. Simple. Therefore, total moment of inertia, integral di is equal to integral dm into x square. Integral di is I. Integration means we have to put the limit from the origin left, right. That is minus L by 2 to plus L by 2. So I can write I is equal to integral minus L by 2 to plus L by 2 dm x square. What is dm? Lambda into dx. Lambda into dx into x square. Lambda is a constant. Take it out. So I can write I is equal to integral lambda you have taken out minus L by 2 to plus L by 2 x square dx. X square dx integration is x power 3 by 3. x power n dx is x power n plus 1 by n plus 1. Here x power 2. So we are putting x power 2 plus 1 by 2 plus 1. X power 3 by 3. So I can write minus L by 2 to plus L by 2. So I is equal to lambda by 3. Instead of x, you put L by 2. L by 2 the whole cube minus, instead of x, you put minus L by 2. Minus L by 2 the whole cube. Substitute. What will you get, ma? I is equal to lambda is m by L. So you will get m by 3L. L by 2 the whole cube. L cube by 8 minus L by 2 the whole cube is minus L cube by 8. So minus minus plus L cube by 8. So L cube by 8, L cube by 8, you are going to calculate. What will you get, ma? M by 3L, 2L cube by 8. 1L get cancelled here. 2 and 8 means 4 times. So you will get M by 3 into L square by 4. So ML square by 12. Moment of inertia of a rod. For an axis passing perpendicular to its length at the center is I is equal to ML square by 12. Very important 5-mark question. Moment of inertia of a uniform rod. Next, we are going to talk moment of inertia of a uniform ring. Uniform ring, circular ring. Sir, this is a ring. This is the axis of rotation. Radius of the ring, you take it as capital R. As usual, small portion we are considering here, dx. The mass of that small portion is dm. So, in this case, moment of inertia of the small portion, similar to rod discussion, is di is equal to dm into, what is the distance here? Distance from the axis of rotation is nothing but radius here, that is dm into r square. There we have taken lambda is the mass per unit length of the rod. Here lambda be the mass per unit length of the ring. Mass by length. Same M by L. But here the length is nothing but the circumference. The circumference here is 2 pi r. Because the ring we are considering, small portion of the ring you are taking. When you take the small portion of the ring, that is nothing but the circumference of the ring. So the length becomes the circumference here. So m by 2 pi r. What is the next step? We have to calculate dm. Mass by length is lambda for total mass by total length. Small portion dm is lambda into L. So that is lambda into 2 pi r. Not 2 pi r. For the small portion, the distance is dx we will take. 2 pi r for the entire. This portion only we want mass. So that is lambda into dx. Our aim is to calculate the moment of inertia for the entire ring. Entire ring means what limit we have to put? Limit of integration. Here we are starting full ring. So starting with 0, full ring limit. Therefore, total moment of inertia is I is equal to integral dm into r square, limit 0 to L. I is equal to integral L is nothing but 2 pi r dm into r square. What is dm? Lambda into dx into r square. Correct? So I is equal to lambda r square, you take it out, integral 0 to 2 pi r dx. Lambda r square into integral dx is x 0 to 2 pi r. Upper limit minus lower limit. What is lambda ma here? So I can write lambda is m by 2 pi r into r square. Upper limit 2 pi r minus 0. 2 pi r cancels. So we will get I is equal to m r square. Moment of inertia of a ring for an axis passing through the center perpendicular to the plane is I is equal to m r square. Correct? Simple concept. Ring is different, disk is different. Next, we are going to talk uniform disk. Moment of inertia of a uniform disk. Moment of inertia of a rod, we have seen. Second, we have seen moment of inertia of a ring. Third, moment of inertia of a disk. Origin, radius, you take it as capital R. You are considering a small portion here. Small portion of the disk you are considering. Definitely disk means we have got some thickness here. We have got some thickness. So that small portion, this is a small portion. You are taking out from the disk. That small portion we have to consider. That small portion distance, radius is capital R. That small portion distance, total radius is capital R. Small portion distance, you can take it as small r. Up to the extreme, the radius is capital R. Small portion distance from the axis of rotation, you take it as small r. What is the thickness of the ring or thickness of the disc? Let us assume the thickness here is dr. Dr is the thickness. In the case of a ring, we have not taken into account the thickness of the ring. Here disc, it has got some area. So when you consider that small portion, it has got some thickness. But the basic formula, moment of inertia of the small portion, as usual, what is the formula? Di is equal to dm into distance from the axis of rotation, that is small r square. Here, sigma be the mass per unit area. In previous two cases, we have taken lambda is the mass per unit length. Wire or rod, we have not taken the thickness into account. Ring thickness, we have not taken into account. But in the case of a disc, thickness should be considered. So it should be mass per unit area. What is area? Mass by area, we have to write sigma is equal to m by area. Circular area only, so pi r square. Simple. For a small portion, dm into r square, we have to calculate. What is dm? We have to write first. Sigma into area. That small portion circumference. Sigma into 2 pi r into the thickness. What is the thickness here? Dr. Why we have taken dr as a thickness, man? See, in this disc portion, small portion of the disc, entire disc you have, small portion only you are considering. In that we have a thickness dr. So that total value 2 pi r circumference into the thickness will be the area there. Sigma into area means pi r square we have to take for the entire disc. Small portion only we need. So it should be 2 pi r, small 2 pi r into the thickness dr. Therefore, di is equal to dm, that is sigma into 2 pi r dr into r square. So I can write sigma 2 pi r cube dr. Okay. So total moment of inertia is integral sigma 2 pi r cube dr. Integral, what is sigma? M by pi r square into 2 pi r cube dr. Pi get cancelled. You will get, you should put the limit of integration. Limit is very simple, 0 maximum, 0 to R, that's all. So I can write I is equal to M, 2M by R square, take it out. Integral 0 to R cube dr. What is R cube dr formula? Ma? Integral x power n dx we wrote x power n plus 1 by n plus 1. So I can write R cube dr, that is 2m by r square into r power 4 by 4, limit 0 to r. So 4 means 2 and 4 cancels, you will get m by 2r square. This is r power 4 minus 0. R power 4 r square cancels means half mr square. So moment of inertia of a disk is mr square by 2. Moment of inertia of a ring is mr square. Moment of inertia of a rod is ml square by 12. Here, one big change is mass by area we have to consider. So new term, mass sigma we have to calculate. Mass per unit area. Previous two cases, mass per unit length we have done. Now mass per unit area. Correct? So we have seen moment of inertia, basic concept, radius of gyration, and moment of inertia of three different rigid bodies: uniform rod, disc, and a ring. Three things we have taken. Okay. Now, related to this, problems we are going to discuss. Problems related with moment of inertia, radius of gyration, and all the three rigid bodies we are going to talk. We'll go to the problem.